If you've watched my previous videos, you're probably aware that I do a fair amount of chemistry on this channel, and there's a good reason why. You see, semiconductors require chemicals that are both extremely expensive and often simply not sold to amateurs like me. The easiest way for me to get my hands on these critical chemicals is to make them myself. But chemistry can be risky. Chemicals can range from totally safe to stupid dangerous, and even if they aren't, the chemicals used to make them often are. Take sodium chloride, table salt, for example. It's safe to eat, but one of the ways to make it is to react sodium, a metal that explodes on contact with water, with chlorine, a literal chemical weapon. So obviously, if we are doing chemistry, we want to do it in a manner that is as safe as possible. And to be honest, I have fallen short of that goal. If you saw my video on nanoparticles, then you probably remember I accidentally filled my lab with a moderate amount of hydrochloric acid fumes. Fortunately, I was wearing protective gear and had decent ventilation, so I wasn't personally harmed. But after this incident, I made it my immediate goal to improve my lab safety. And the biggest step in that direction was to acquire a fume hood. So for anyone who doesn't already know, a fume hood is easily the most important part of any chemistry lab. Simply put, a fume hood is a box with an exhaust fan, inside of which chemical reactions are run. The fume hood protects the chemist in two main ways. First, the exhaust fan removes dangerous vapors, and second, the fume hood acts as a shield in case of chemical spills, splatters, or even minor explosions. So after I cleared the hydrochloric acid vapors from my shop and decided that I wanted a fume hood, my next decision was, do I buy one or make one myself? I checked the prices on new fume hoods and, oh boy, these are pretty expensive for a hobbyist. I've seen a bunch of videos online of people successfully building their own fume hoods from cheap plywood and a blower fan, so maybe I should just go that route. Well, it turns out there is a bit more to a fume hood than just a box with a fan in it. Fume hoods are designed not to simply suck out the air, but to do it in a way that ensures that absolutely none of the vapors can escape. You see, if you are working with something truly deadly, you want to be darn sure that none of it gets out. So you might think, okay, just use a really big fan with a ton of airflow. But actually, that doesn't work. You see, when air moves too quickly, it becomes turbulent, and this erratic air movement can cause small regions where air can leave the fume hood. Chemical fume hoods are designed to maintain something called laminar flow, where all of the air moves smoothly in one direction, ensuring that absolutely no dangerous vapors leak out into your breathing space. Now, any fume hood, even a cardboard box with a fan in it, is better than nothing. However, the laminar flow of a real chemical fume hood is valuable and allows for greater safety when handling potentially dangerous chemicals. And this is why industrial and research chemistry labs always have these professionally designed fume hoods. And so I contemplated the question, what about a used fume hood? Wouldn't there be contamination concerns? Would I get poisoned? So I did some research, and it turns out that yes, laboratory equipment is often decommissioned, and there are actually recyclers out there that specialize in just this kind of equipment. I'm lucky enough to live near Silicon Valley, so it turned out that there were more than a few of these recyclers near me. I got in contact with one of them, and they explained that there are several different regulations requiring equipment to be cleaned before it is removed from a lab. Notably, OSHA requires cleaning to protect workers from dangerous chemicals, and the EPA requires cleaning to ensure that hazardous waste doesn't enter the environment. Okay, so this is reassuring. It seems like, at the very least, a used fume hood should be relatively clean. So I looked around and managed to find a recycler near me with a hood that had just been cleaned and was ready for sale. I went to check it out in person, and holy crap is this thing huge. It was about 7 feet long and over 800 pounds. No way I could fit this in my garage. It certainly was nice, though. I politely declined and thanked them for their time. But as I was about to leave, I noticed a smaller hood in the corner. Apparently, they hadn't mentioned it earlier because it had just arrived and was in such poor shape that they expected to just scrap it. I spent a few minutes checking it out, and honestly, it seemed pretty functional. I offered them $200 for it, and they accepted immediately. I borrowed a truck from a friend, and the recycler loaded the hood onto the bed using their forklift. I then carefully tied it down with ratchet straps and drove it home.
Oh dear. Classic San Jose apocalypse.
I love how it never rains in California, except on days when you move heavy equipment. Just my luck. Well, anyway, after the rain stopped, getting it off the truck was not easy. After some effort, we managed to slide it safely down a couple of ramps and got it into the garage. I immediately went to work stripping the hood and removing everything I possibly could, both to clean it, but also to lighten it so that it would be easier to move later. Remember, this hood needs to be lifted onto a table in order to be at a useful height. While I was taking off one of the interior panels, I ran into a bit of a problem. Well, I suppose I should have expected this. Just to be clear, I don't blame the recycler for this. Whatever lab removed the hood evidently didn't clean it fully beforehand. So, this looks worse than it really is. Most of this is just dust. I saved a small sample, and then thoroughly cleaned the rest of the inside of the hood, and showered off for good measure afterward. Honestly, the worst part of this cleanup was removing this giant sticker from the front glass. Now, that's unforgivable. One of the few things on this hood that was actually broken was the ventilation duct. I assume this was damaged when they removed the hood from its previous location. Fortunately, it's a fairly easy fix. I was able to find a replacement 12-inch duct with a flange large enough to fit this hole. The flange came with pre-drilled holes, but the pattern didn't match the fume hood, so I had to do that myself. I just installed the vent, then put one of the screws in, and transferred the pattern by drilling through the existing holes in the fume hood. That way, all the bolt holes will line up perfectly. And just like that, the new duct is installed. Now that that's taken care of, we need to figure out how to mount the fume hood. Speaking of, what kind of surface is this thing supposed to sit on anyway? Well, after a lot of searching, I managed to locate an installation manual for the hood. In the manual, it specifies the dimensions of the table and the work surface the hood is supposed to be mounted on. You can see here that it is to be mounted on a cabinet with a work surface exactly 31 inches by 59 3/4 inches. Now, I initially thought I was just going to buy a cabinet for the hood, but because of the very specific dimensions and also how heavy this thing is, I decided instead to weld my own table from square steel tubing. I've actually made a number of welded tables for my lab already, and have been really happy with the results. Welded steel is just so much more sturdy than anything that has to be bolted or screwed together, and so I decided to go this route for the fume hood as well. This table is to be made primarily of 1.5-inch square steel tubing with 1/16 inch walls. By the way, if you've never welded before, well, first off, you should totally learn because it's an extremely useful skill, but second, you should know that it can be tricky. You see, this table is made up of a bunch of different pieces that need to be welded at exact 90-degree angles to each other, and it can be surprisingly difficult to achieve that. This is because welding happens at extremely high temperatures, and so, as the weld cools down, the part you just welded contracts slightly and can pull other parts out of their precise alignment. Now, I'm not a particularly good welder, but I have found that for most skills, you can usually trade time for experience. To that end, I made sure to first tack each joint with spot welds, then check the angles. If any of the angles were not perfect 90 degrees, then I'd use a hacksaw to break the offending tack weld and try again. By being slow and methodical, I managed to ensure that all of the pieces were tack welded at the proper angles before doing the full welds. That gave me the best shot at keeping everything nice and square. Alright, the top of the table's done. Now onto the legs. I'm using some 1/8-inch thick steel tubing for the legs because I had some spare. It's total overkill though. Same strategy as before. Tack first, then measure, fix any mistakes, then do the full weld. And repeat that about 100 times until you have a finished frame. I sanded the steel to roughen the surface so the paint would adhere better, and wiped down with acetone to remove any dust. Then I applied a coat of primer and 2 coats of flat black paint. For the top surface, I cut a piece of 3/4 inch plywood to size, painted it black, and applied several coats of polyurethane. As an aside, most fume hoods use a solid epoxy tabletop because of its superior chemical resistance, but those cost a lot. If it turns out that the polyurethane is not sufficient, I will try pouring a layer of epoxy resin on top of this piece of wood and see if that works well enough. Anyway, this table also has 2 large shelves underneath the main surface for storage. And for that, I just used some inexpensive chipboard. Once it's painted and coated with polyurethane, no one will know how much of a cheapskate I am. One thing that you don't want to cheap out on, though, is the feet that this whole thing rests on. I installed some good quality leveling feet, as well as some solid caster wheels so that I can move this thing around easily. Alright, it looks like this table is ready for action. Okay, so I have the table, and I have the hood, but how do I get the hood onto the table? I consulted the manual again, and it said, and I quote, "Using as many workers as needed, lift assembled fume hood and place onto leveled work surface." Really? Wow. Just so that we're clear, these are instructions for all of the fume hoods in their lineup, all the way up to the monsters that weigh over 1,000 pounds. Well, fortunately for me, I had already removed a ton of weight stripping the hood earlier, so it was probably only about 200 pounds or so in its current state. I got 3 of my pals to help, and we managed to lift the hood onto the table using the power of friendship. Now that the hood was in place, it was just a matter of screwing it down to the table surface. I think this hood used something like 28 screws total. Kind of crazy. I think I would have preferred a few bolts, but I guess these screws are less structural and more for just keeping the hood in place on the tabletop. Alright, now that the hood is mounted, let's figure out the ventilation. It's standard practice in labs to use solid ducting for fume hood exhausts, but flexible duct is much easier to work with. Aluminum ducting is most common, but it's unsuitable for our use case because it would deteriorate in the presence of acid vapors. PVC, on the other hand, is a very chemically resistant plastic, and so is well suited for this task. Cheap, thin-walled PVC ducting is plentiful, but I decided to spend a bit more money on thicker, more puncture-resistant PVC duct. It's a bit expensive, about $10 a foot, but it's way more durable than the cheap stuff. For the exhaust fan, I picked up this 14-inch can fan from Craigslist. They are extremely common industrial fans for things like hydroponics, and so they can often be found used for $100 or less. They are actually remarkably quiet for the amount of air they move. Take a listen. Pretty good, honestly. At maximum speed, this thing can move 1,700 cubic feet per minute. I bought this small anemometer and verified that the fan was indeed reaching its stated airspeed, though I think it was already obvious that this thing moves a ton of air. And as an added bonus, its speed can be controlled with a variac, so I should be able to dial in the exact airflow that I want. The exhaust port in my lab is rectangular, so I'm building a plywood housing that will adapt the circular fan to the rectangular vent hole. There's not too much to add about building this thing. It's just some 3/4-inch plywood and some screws, though I probably could have made it look a little less like a toilet seat. This'll do. Okay, installation time. This is one of the vents in my lab. Ideally, I'd exhaust higher up, but this is the best I can do without tearing out a wall. Also, for those who might be concerned, there are more vents on the other side of the lab, so covering up just this one shouldn't be too much of a problem. To avoid any leakage, I filled all the gaps with drywall putty. This should ensure that all of the fumes are vented outside, and none leak into the lab. I connected the other end of the duct from the fume hood, and now we're almost ready to test this thing. One thing to fix first. The hood didn't come with both side panels, so I had to make one myself to plug the side access hole. I found a suitable piece of some kind of plastic in my scrap bin, and cut it to the correct size and shape on my milling machine. Alright, let's see if I measured correctly. Nice. I added a couple of mounting bars to fix it in place. Easy peasy. I very nearly forgot to reinstall the rear baffles. I also decided to replace the old fluorescent tube lights with LEDs. Fluorescent lights require a ballast, but these LEDs require it to be removed. Once I finished rewiring the housing, I replaced the lights, and everything looks good. I went ahead and reinstalled the overhead fixture, and I also rewired the hood to control each tube individually. Nice. The hood is really coming together now. One more thing we need to do is to seal the surface of the fume hood. As it stands right now, any spills in the fume hood would leak out through the gaps in between the table surface and the hood walls. We need a sealant to stop that from happening. Now, the correct material for the job is a fluoroelastomer caulk. The fluorine in the caulk gives it a superior chemical resistance, but this stuff is expensive. Silicone has a reasonable chemical resistance, so I'm going to use that for now, and upgrade later if it turns out to not be sufficient for my needs. I've never actually done this before, and I'm sure I'm probably not using proper technique. But As long as it forms a decent seal, I don't really care all that much about aesthetics. I sealed up the rest of the table and laid down a bead in the front here to form a shallow lip to catch any small spills. Okay, we could call the fume hood done right here, but there's actually a couple of important additions we can make that really improve your quality of life when using a fume hood. The first is to get a lab rack. This is a set of horizontal and vertical bars that you can attach clamps to in order to hold your chemistry apparatus. Normally, you'll see people using a few stands such as these. These stands are pretty easy to bump if you aren't being careful, and knocking one over is a great way to end up drenching yourself in chemicals. It's common in labs to have a rack built into the fume hood to both improve safety as well as to increase the number of potential mounting points. But, as you might guess, these are expensive. The ones I found were around $1,000. Maybe I can make one instead. Every lab frame is made of 3 different components. We need long rods, clamps to attach the rods together, and flanges to attach the rods to the table. Let's start with the long rods. I'm using 1/2-inch diameter 3/16 stainless. I cut it in the bandsaw, and I'm using the lathe to finish the ends to final length. This is probably the longest piece I've ever used in this lathe. Fortunately, it fits through the spindle bore. Alright, let's spin it up and face the ends. Okay, that doesn't feel safe at all. I need to stabilize this real quick. I just need to keep it from flopping around so much. Let's see if the quick and dirty solution works. Moment of truth. That's acceptable. Now that that's under control, it's time to clean up the ends and trim them to length. And repeat that 6 more times. Done. Now let's tackle the flange that mounts the lab frame to the table. Once again, 3/16 stainless, this time 1.5 inches in diameter. In case you're wondering, I'm using 3/16 stainless because it's one of the best alloys for chemical resistance, which is obviously important for a chemical fume hood. Oops. Well, that's awkward. The stock's too big to fit through the spindle bore of my 3-jaw chuck. Let's swap that out for the 4-jaw and try again. Well, at least the 4-jaw can accept the stock, but it's still bottoming out on the spindle bore of the lathe. Maybe we can get away with it. Okay, that's sticking out way too much. In times like this, the steady rest is really the only option left. Well, that was a lot of setup. Time to actually make our part. I start by facing the end to form a flat surface. Then I do turning operations to shrink the diameter and form the shape of the flange. Now we need to drill a hole in the center. 3/16 stainless is a tough alloy and is hard to drill, so I'm making sure to step up the drill size in small increments until I reach the final diameter. I definitely exceeded the temperature limit of the lubricating oil I was using. These are the kinds of operations where I really wish I had flood coolant. The chips aren't turning yellow or blue though, so I think the temperature is not high enough to damage the edge on the drill bit. Alright, this side of the flange is done. Now I need to part this off. Normally, for aluminum, I'd use my lathe, but this is a very large piece of very tough material for a small lathe. Much easier to just use the bandsaw in this case. All I need to do is clean up the reverse side, and our flange blank is done. All that's left now is to take it over to the mill and put some holes in it. I used the mill to drill the 4 smooth holes in the base of the flange, and then drilled and tapped the hole for the set screw on the side. And then repeated the whole process 9 more times. The last parts we need to make are the clamps that hold the horizontal and vertical bars together. I start with a piece of 3/4 inch round rod, and then face one end on the lathe. Then I blue the surface, and use a cheap pair of calipers to mark a piece exactly 1.6 inches long. This allows me to take it to the bandsaw and cut it off more accurately, as well as reduce waste. Then I put it back in the lathe and take a light facing cut on the other side to clean it up. These clamps have to all be exactly the same size, or else they won't align with each other. So I'm taking my time and ensuring that every single one of them is the same length. Nice. Now we need to machine the hole and the slot that the bars go through. I think it's going to be easier to do the hole first. I'm using a collet block to hold the blank, and center drilling first to make sure that the hole is on target, and once again stepping up in small increments to the final drill size of 1/2 inch. Now that we've done that, we need to cut the slot so that it's exactly 90 degrees offset from the hole. And when I say exactly, I mean exactly. Eyeballing this is not going to be accurate enough. But I think I have a solution. I made this little insert that goes directly into the hole, allowing us to clamp the part with the existing hole facing directly against the vice jaws. allowing us to drill our next hole exactly 90 degrees from the previous one. Then we can open that hole up with larger drills, and then come in from the side with an end mill to finish the slot. Perfect. It looks like the slot and the hole are exactly where they need to be. Now all we need to do is drill and tap the holes for the set screws, and we should be good to go. I ended up using the lathe for the holes on the other side because they're directly on center. The lathe chuck automatically centers parts for you, so it's easier. Let's see if the set screw is strong enough to hold the bar in place. Okay, the rod slides in nicely. Now let's tighten the set screw. Yep, that's not going anywhere. Alright, all the parts are done. Let's install it in the hood. I marked a line in the hood where I think the rack should go. Then I installed only one of the flanges. I then put down the remaining flanges in a line, but didn't screw them in. Then, separately, I put the rest of the frame together. This allows me to use the frame itself to ensure that all of the other flanges are perfectly in a line. Remember, this frame is made of 1/2 inch solid steel bars, and they will not flex to accommodate any misalignments. I adjusted the clamps until the horizontal bars were level. Then I marked the position of the holes for the flanges on the side walls. I pulled out the lab frame, and then drilled the holes for the flanges on the table's surface, as well as the holes I had marked on the hood's walls. Now we're ready to do the final installation of the lab frame. It's important that no chemical spills can seep in under these flanges, so I'm giving them a nice dose of silicone to seal them. I finish installing all 4 of the screws on each of the flanges, and then wipe away the excess silicone. Then I bring the frame back into the hood, and carefully slot it into the bottom flanges. Nice. If I've done everything right, then the holes for the wall flanges should align perfectly. Moment of truth. Nice. I installed all the rest of the screws, and it looks like this lab frame is ready to go. Alright, let's see how stiff this thing is. Wow, that is incredibly sturdy. I'm pulling hard and this thing's not flexing at all. The frame looks great. I'm really satisfied with this. There's just one more thing this fume hood needs. It's really common to need a source of cooling water when running chemical reactions, such as for this distillation condenser here. I would like to have a source of cooling water handy in the fume hood as well. So I went back to the lathe and whipped up a few of these hose fittings. Compared to the lab frame, this is easy mode. I kind of just arbitrarily chose a location I thought was convenient. I think you can put them wherever you want. And there we are. Okay, time to connect these fittings to the water chiller. I should probably also label the connections in the fume hood so that I don't forget which one's which and accidentally connect it backwards. I'll replace the Sharpie marks with a proper label soon. I filled the chiller with water and hooked up a simple water loop, turned on the pump, and everything looks good. No leaks. I installed the remaining 2 fittings on the other side of the hood to serve as an air and vacuum line. Now that everything's installed, we can finish by putting the exterior side panels back on the fume hood. Oh dear, I didn't notice earlier how warped these things are. Well, some quality time with a dead blow hammer ought to fix that right up. That's better. Let's get these back on. Man, these panels have to be at least 30 pounds apiece. I am so glad I took these off before lifting the hood onto the table earlier. Just gotta reattach the duct real quick. And we're done. We did it. The fume hood is complete. There's just one more thing that needs to be done now. We went through all of this trouble to restore this critical piece of lab safety equipment, and now we have to verify that it actually performs its task. We need to validate that it's actually moving the air correctly. The minimum recommended flow rate for a fume hood is between 80 and 120 linear feet per minute. Any slower than that, and we can't guarantee that the fumes will be evacuated quickly enough. Using the anemometer, I measured the airspeed at the opening of the fume hood. I then opened the sash 2 inches at a time and repeated the measurement. The result is this pretty graph here. You can see that the airflow is greatest when the sash is nearly closed, and slows down as you open the sash wider and wider. It seems that at around 18 inches, the airflow finally dips below 80 feet per minute. So that means that at 18 inches is the maximum I can open the sash and still guarantee that the airflow is in the safe range. I marked the location on the fume hood, so I'll know not to open the sash any wider than that for future reference. By the way, all fume hoods come with an airflow sensor to warn you in case of a fan failure or some other kind of downstream blockage. Now, given that the fan is literally right here, one would hope that I would notice if it stopped working. However, I might as well test the alarm just in case. It should register the failure after about 15 seconds. Cool. It's good to know that this feature still works. You never know when you might need it. Okay, one final test. I want to check to make sure that the airflow is nice and smooth across the hood. I borrowed this little smoke machine from a friend. These are for leak testing the engine intake of a car. Let's see if we can use it to visualize the airflow in the fume hood. Nice! This is the reason I wanted a proper fume hood. You can see that the air moves directly backwards in the fume hood, and there are no visible vortices or other turbulence. This is how we ensure that no wisps of dangerous vapors can exit the hood. This is why it's so important to have the airfoil and proper baffles inside your fume hood. It's this laminar flow that makes a professional fume hood so much safer than just a box with a hole in it. Even if I open the sash a lot wider, the airflow still looks nice and smooth. It's even excellent at pulling in vapors from outside the fume hood itself. That's really impressive, honestly. Super satisfying. There's something really mesmerizing about watching this. Just for fun, I decided to fill a bag with the smoke so that I could dump it out all at once. Let's see how the fume hood handles it. Awesome! Well, that about wraps it up for the fume hood. I'm super excited to have a cool new piece of laboratory equipment for future chemistry projects, and I'm sure my lungs and eyes are going to be happy too. Thank you so much for watching. I want to especially thank my Patreon patrons who support me and make projects like this possible. If you liked the video, feel free to subscribe and ring the bell to get notified when my videos are published. Thank you for watching, and have a nice day.